So graphing rational functions. We touched on the general form of a rational function in 3.1. We're going to go over it again here in 3.2. I don't think I called it general form, but it's what we use for transformations. So just like when we look at transformations of quadratic functions and transformations of absolute value functions, I have kind of these rules that'll help me figure out what this graph would look like. Now we're mostly just going to use general form to talk about transformations. It's not a very convenient form for graphing. Well, it works okay for graphing. Okay. So just like before, if the absolute value of A is greater than 1, this causes a vertical stretch. If A is between 0 and 1, it causes a vertical shrink. And how you'll see this affect the graph is it's going to move these anchor points. Right? If I have a negative, then that causes a reflection across the x-axis. The h will cause a horizontal shift. So if it's a minus h, then it's going to be a shift right. If it's a plus h, it's going to be a shift left. And this is actually going to change the horizontal asymptote. The vertical asymptote. 0 shifts right. Vertical asymptote is going to be x equals h. A lot of information there. So we'll watch as h changes. So if I have like x minus 2, then that's a shift right 2 and a vertical asymptote of x equals 2. If it's a minus h, if I have like x plus 5, then that's a shift left 5. We're going to get a little practice with long division here. Now there are some circumstances where you could use synthetic division. I'm going to go with practicing long division because it's always going to work. But you could do this problem right here with synthetic division. Rewrite the function in general form using long division. State the asymptotes. An example A, g of x is equal to 4x divided by x minus 2. The divisor goes outside. The numerator goes inside. Now I'm missing my constant here, so I'm going to fill it in, the 4x, right? That's just a linear term. I don't have a constant, so I'm going to put a placeholder in there. It's a pretty short division problem. So when I start off with long division, I have x into 4x. So if you have to do that on the side, that's fine. 4x divided by x simplifies to give me 4. I'm going to put that in this spot here. First I divide, then I distribute. So I multiply through and I have 4 times x. 4 times negative 2. When we change the signs, so 4x minus 4x, that cancels. Wonderful. And then 0 plus 8 gives me 8. I have nothing left to bring down, so that becomes my remainder. So when I rewrite this, I get 4 plus, and my remainder is 8. My remainder is 8 divided by x minus 2. I'm just going to try rework that just a little bit to get it to match the general form. And in the general form, you'll see that the fraction comes first and the whole number comes behind. So I'm just going to swap these. So just using prior knowledge of long division and then getting a little creative with rewriting that in a different form. All right. Great. So the second part of this says state the asymptotes. So checking out what I've got here. Now I could go through and I could name all of these transformations. 8 causes a vertical stretch with a factor of 8. The minus 2 causes this graph to move to the right 2. And the plus 4 causes this graph to move up 4. The other thing that I can do, what it specifically asks for, is to state the asymptotes. So this right here causes the graph to move right 2. And if I look up here at my key, then I have a vertical asymptote at x equals h. So I'm going to have some asymptotes. So I have an asymptote at x equals 2. And then because this shifts the graph up 4, I did have an asymptote here at y equals 0, but if I shift the graph up 4, then that's going to become y equals 4. So somebody in 5th period last week said, okay, so basically the number next to x always lies and the one out here always tells the truth. And I was like, yeah, you can think of it like that, right? This one's always backwards. If I have x minus 2, that actually means I have x equals positive 2. And a plus 4, if this one tells the truth, I'm going to go up 4, right? I don't have to change the sign. Questions or things I can clarify? We're going to do another one of these, so you'll see it again. Anything that I can add some explanation on? Okay, so second one. Now I told you that for A, you could use synthetic division. And it's true you can, because when what you're dividing by is x minus 2. Remember, when I'm doing synthetic division, I have to have just x plus or minus a number. For B, you can't use synthetic division for this type of divisor. This divisor is 2x minus 1, so I have to use long division. Same exact process. We'll just get a different result. So I'm going to set you up and then I'm going to pause and let you work this out without my assistance. So it's going to be 6x, and since I don't have a constant, I skip over that value. I'm going to put a 0 there. So see if you can just do the long division part. So if you do this correctly, you should have a remainder of -3. All right, so when I start my long division, I'm putting 2x into 6x. So 2x into 6x. Well, let's see. If that's a little tough to wrap your mind around, remember just to write it on the side, do a little division. The x's cancel, and 3 goes into 6 2 times. So I get 2 here. I'm going to put that in my column for just numbers. And then I distribute 2. Whoops, that's not 2. Wait a minute, what did I do? Oh, I wrote it down wrong over here. Cool, let's try that again. It's 6x divided by 2x. I'm getting ahead in my mind and then making mistakes. The x's cancel and 2 goes into 6 3 times. That works better. So 2x into 6x goes 3 times. And then I distribute. 3 times 2x is 6x. 3 times negative 1 is minus 3. When I was grading the tests on this, the most common error was not changing the signs. Sadly, saw it over and over and over again. If you have to use something of another color to remind you to do it, go for it. Do what works. Positive 3, right? I think my previous notes are wrong. I think it's positive 3. Oh, you know why it's turning out wrong? It's because I wrote the problem down wrong initially. That's why. That's okay. This will work. Okay. So I get 3 goes in with a remainder of 3. So my remainder gets divided by my divisor, 2x minus 1. And I'm going to rewrite that. So f of x is my original function, so I'm just going to use f of x. And I'm going to put the fraction first, and then the remainder. So the remainder is positive 3. So there is my equation in the general form. And now let's talk about asymptotes. So the shift here is a little bit more difficult to see. So I was taking my time previously, and I was taking whatever factor had this x and setting it equal to 0 and solving. So I'm going to do that here to get the value of x. We talked about how up here it's just really easy, just use a shift. But this time you might want to do a little bit of solving an equation. If you do that in your head, that's totally fine. So I get x is equal to 1/2. So when I'm looking at asymptotes, instead of on my parent function when I have x equals 0, this shifts to the right 1/2. So I have x equals 1/2 is going to be my asymptote. And then the plus 3 at the end shifts my graph up 3. So instead of being at y equals 0, I'm going to have an asymptote at y equals 3. All right. So that's basically one type of problem. We're going to get into another type of problem, but I've got a bunch of notes for you to copy down first. Well, I don't know if that's a bunch, but it's a few big ideas. So here's the formal definition of a rational function. It's a function defined by a ratio, hence the word rational, of 2 polynomials. So basically, a rational function is equal to a polynomial divided by a polynomial. A reminder, polynomial is anytime you have x to the power of some number, or even just a constant. And the trick here is that the denominator, q of x, cannot be 0. Ever, ever, ever. We've been talking about how these asymptotes are these invisible lines that the graphs approach, but do not cross as they go to infinity. A vertical asymptote is caused by zeros of the denominator that don't cancel. Vertical asymptotes are always going to be equations like x equals some number. The parent function is x equals 0. Holes, which are a new idea that we haven't talked about yet, are caused by zeros of the denominator that do cancel. They are also written as x equals some value. Horizontal asymptotes follow their own rules. And we'll dive into that a little bit more. But the way that we're going to use that is we're going to use y is equal to a over b, where a and b are coefficients of the greatest matching exponents. Let's just say matching. Proper grammar. And horizontal asymptotes always look like y equals some number. Vertical asymptotes and holes together make up what's called the points of discontinuity. More advanced language for you. Points of discontinuity. Just the vertical asymptotes and the holes. So example 2, identify vertical and horizontal asymptotes and holes by hand, and then use Desmos only to help you graph. So a big part of this lesson is going through and factoring all of the polynomials. Using all of the different ways that we know how to factor. So problem A, f of x is equal to 2x squared minus 4x, all divided by x squared minus 4. So I'm going to factor the top and I'm going to factor the bottom. The first step in factoring is to always take out the greatest common factor. So when I start working on the top here, I can rewrite that by taking out a 2. They both have a 2 in common. They both have an x in common. And when I rewrite that, let's see, I have 2x squared divided by 2x. I'm left with an x. And then a minus 4x divided by 2x. I'm left with a minus 2. Okay, so the top factors to 2x times x minus 2. That one's not a quadratic trinomial, so I don't have to do the long way. And x squared minus 4. X squared minus 4 is actually a difference of squares. So we practiced talking about how if I have a squared minus b squared, then I can factor that really quickly to a plus b times a minus b. So this gets factored to x plus 2 times x minus 2. So prior knowledge there that we've been trying to work on over the course of the past 11 weeks. We're in week 12 already, you guys. Crazy. Okay. So what happens is in this graph, whatever factors I have in the denominator call what's called points of discontinuity. A point of discontinuity is a place on the graph where the graph is not continuous. Discontinuity, right? Not continuous. So all that does is it creates some gaps. So for example, this parent function right here has a point of discontinuity at 0. Doesn't exist. It doesn't exist anywhere at 0. So what I'm going to do is I'm going to take each factor in the denominator and I'm going to set each factor equal to 0, solve for those values, and then I'll determine what kind of a point of discontinuity it is. So it could either be a whole or it could be a vertical asymptote. So I'm going to take each one of these. X plus 2, only the ones in the denominator, and x minus 2, and I'm going to set those equal to 0. Only the factors in the denominator. The factors on top do important things too, but they don't affect where the points of discontinuity will be. And then I solve these little mini equations. This graph has 2 points of discontinuity at x equals negative 2 and x equals positive 2. to determine what kind of a point of discontinuity, right? A vertical asymptote are caused by zeros in the denominator, got that don't cancel. And a hole is caused by zeros in the denominator that do cancel. So now when I go back and I look at this, I have factors on top, factors on bottom. Oh, look, they both have x minus 2 in common. Do you see how that's going to cancel? Just like I cancel numbers, I can cancel factors and expressions. So I have x minus 2. That led me to this 0, this point of discontinuity. If it cancels, right, that's called a hole. So I have a hole at x equals 2. I have a vertical asymptote. The vertical asymptote is caused by zeros of the denominator that do not cancel. This factor does not cancel. Therefore, this point of discontinuity is a vertical asymptote. So much information. We'll talk about what a hole looks like also. We haven't really looked at those. Pause there. Question so far? We still got a couple steps to go. Any questions on how did I factor, or where did I find points of discontinuity, or what does that mean, or how do I know which one's a hole and which one's a vertical asymptote? Okay, the next piece of the puzzle is this idea of horizontal asymptotes, and this is kind of a little bit of figuring here. So I'm going to take the coefficients of the greatest matching exponents. This one's easy because I have greatest matching exponents. So look on top, 2x squared minus 4x, greatest exponent is x squared, cool. On bottom, greatest exponent is x squared. So I'm going to look at the coefficients of those highest matching exponents. Horizontal asymptote is going to be y equals a over b. A is standing for this number 2. B is standing for, well, there's not a number there, but that's just going to be a 1. So my horizontal asymptote is going to be 2 over 1, or we usually just write that as 2. A lot of information. And I still get to graph. So I'm going to go ahead and start building my graph. I know my boxes are really small. I'm going to keep them counting by ones just because sometimes it's a lot easier to follow. When we start counting by halves or twos, it gets a little trickier to keep track of. And I'm going to draw in my asymptotes to start with. So I have a vertical asymptote at x equals -2. X equals, remember, is a vertical line. So I go to the x-axis, I go to -2, and I'm going to draw a vertical dashed asymptote line. And that's x equals -2. Then I have a horizontal asymptote at y equals 2, so I go to the y-axis at 2, and I draw a line through y equals 2. To get that part of my graph. Give you a moment to catch up, and then I'm going to navigate away from this. I'm going to go to Desmos. And I'm going to graph this function. Now, Desmos, just like other graphing apps, they're not going to graph the asymptote for you. But we talked about how I have an asymptote at y equals 2, which makes sense if I zoom out. I lose some of my detail because I'm in projection mode. If I were to zoom out, you would be able to tell that the graph approaches this line y equals 2 but doesn't cross it. And then the same thing with x equals -2. It approaches this, but it actually doesn't cross it. Now, what Desmos is going to do is it's going to give me a couple good pieces of information. It's going to tell me some anchor points so that I can be really accurate in my graph. This looks like it's going to be my anchor point here. I'm looking for any point that like falls on a nice whole number so that I can just kind of use that and then graph from there. So I've got -4, 4, and then here I've got 0, 0. So I'm going to use those. I will come back to this because we need to talk about the whole. So I said -4, 4. -4, 4 was an anchor point. And 0, 0 was an anchor point. I'm going to use that anchor point and just stay within the asymptotes and kind of draw close to what a rational function looks like. Now I am going to have a little spot in here that I have to erase. Because there's this hole that we haven't talked about. There's a hole at x equals 2. What does that mean? To graph a hole at x equals 2, I'm going to literally... Oh, that's not a very good one. Let me do that again. I'm going to put a little open circle wherever the graph would hit that I hit x equals 2. Why does that happen? It happens because the graph cannot exist at 2. If I plug in 2, I get 2 minus 0 is 0. 0 times something is 0. Anything divided by 0 is undefined. It's a point of discontinuity. The graph cannot exist there because I cannot divide by 0. It doesn't exist. It's undefined. So that's why I get this kind of hole over the graph. And when you look at the graph in Desmos, you're going to see it looks continuous. All right, but it's not because it's a tiny, minuscule little hole. The graph's going to exist at 1.999999999 forever and 2.0000001, but it's not going to exist at this teeny tiny little point. Which is why using Desmos solely is not going to be enough. Because if I look at this, right, the graph looks continuous right here. Now, if you get your point on there well enough, you will see that it'll come up, and I don't know if you can read this typing on there, but it says 2 comma undefined, because that graph does not exist on the of the function. Now that's hard to see because you would have to know exactly where to go to if you don't properly do it by hand. Okay, whew, 1 down. It's a lot. I love it. Pulls so many features together that we've already used. We're going to do more. Doing one of those is certainly not going to be enough for us to really understand. So B, f of x is equal to 3 divided by 2x minus 6. The ways the graph is going to look from here on out will change, but all of the pieces are going to be the same. We're going to factor. We're going to look for points of discontinuity. We're going to decipher whether they're vertical asymptotes or holes, find horizontal asymptotes, and then kind of pick apart the pieces from there. So if you like to kind of have a set of directions, if you like to know what the steps are, the first step would be to factor. The second step is to find the points of discontinuity. I do that by taking the bottom factor, setting it equal to 0. I differentiate which ones are holes and vertical asymptotes. Find the horizontal asymptote. Graph all those pieces, including getting your anchor points from Desmos. Now, do you have to get an anchor point from Desmos? No, you could make a table. All right, so problem B, f of x equal to 3 divided by 2x minus 6. So step 1, factor. Well, the top's just 3. There's nothing to factor there. It's just one term. Yay. The bottom, I have 2x minus 6, and when I go to factor that, I'm just going to look for GCF. I can take a 2 out of both. That leaves me with x minus 3. Not a lot going on in terms of factoring in this problem. Whatever factors I have in the denominator create points of discontinuity. Now, 2 is just 2. I can't set 2 equal to 0. You can only set factors that have an x equal to 0, that have an x equal to 0. So I've got x minus 3. I'm going to take this factor, set it equal to 0. That's going to create a point of discontinuity. When I solve for that, I'll get x equals 3. That's it. I only have one point of discontinuity this time. I differentiate how this point of discontinuity affects the graph by determining whether that factor cancels or not. So, does x minus 3 cancel with something on the top? No. So it's not a hole. It's a vertical asymptote. So in this case, there are no holes. I just have a vertical asymptote. All right, now comes the horizontal asymptote. Horizontal asymptote, a little bit different. I'm looking for terms with the highest exponents that match. So, on the top, I have just a constant. On the bottom, I've got an x and a constant. Great. Here's my term with the highest exponent. But I don't have one above that matches. So I'm going to do this kind of weird thing here. I need something that matches. So I'm going to just kind of think of it as writing into 0x. And I don't usually do this on my paper, but I just want to demonstrate where this is going to come from. So I've got 0 and I've got 2. I need coefficients of matching terms. This gives me a horizontal asymptote of 0 divided by 2. 0 divided by 2 is just 0. I'm going to put whatever pertinent information I have on a graph. A vertical asymptote at x equals 3. And a horizontal asymptote at y equals 0. That horizontal asymptote is going to take a little bit of practice. It's a little funky, but after you see half a dozen or a dozen examples, you'll start to wrap your mind around it. Now I have a general idea on what this graph is going to look like, but I'm going to go over to Desmos, graph it, and try to find out some anchor points to really make it a little bit more specific. This graph doesn't actually hit any whole number, so I'm going to find something that I can use. 4.5, 1. Looks like 3.5, 3. Can't get there though. So 4.5, 1. And 1.5, negative 1. So I'm just going to kind of use those to make sure that this is correct. Let's see, 4.5, 1, 1.5, negative 1. This lets me know how close or how far I am getting from the axis, from the asymptotes. Because sometimes these graphs are really close to the asymptotes and sometimes they're pretty far out. This graph does not have any holes, so I don't need to go back and include any of that. So some things that I'm going to be looking for when we do these graphs. 1, I'm going to be looking for correctly identified hole, vertical asymptote, and horizontal asymptote. You have to be able to do those by hands because you're not going to be able to get them necessarily from the graph. 2, I'm going to be looking for that information on the graph as well as those anchor points and kind of the general shape. All right. I've got 2 more planned to do today. I might mix up D. I might change that one up, but let's see. Definitely want to do C because we want to practice with a factoring a quadratic. So C, f of x equal to x squared plus x minus 20 divided by x minus 4. And this graph kind of has a surprising effect. as we go on and on and on in this course, you're going to see me doing a lot less of all of the small steps of factoring. Because as we get good at it, we need to be able to cut out some of the in-between work and just, work a little bit more efficiently. So when I'm looking at factoring this top, x squared plus x minus 20, first thing I always do when I want to factor is I take out GCF. There's no greatest common factor there. Now, when I would do my product sum, I'd get a product of negative 20 and a sum of positive 1. Those two numbers multiply negative 20 and add to negative 1. 5 and negative 4. Now I can go through from there and I can rewrite the middle terms. Write those in a box. Look for all of the greatest common factors and get that x plus 5 and x minus 4 are the factors. I still use that method when I have complicated trinomials to factor. When I have simple trinomials to factor, I really do these in my head. Which is where I'm hoping you'll be by the end of the year. So when I'm looking for things that multiply to x squared, I have x and x. Because I know these two, when I multiply together, has to give me x squared. And then when I'm looking for two numbers that multiply to 20, when I use that x feature right there, I can have 1 and 20, 2 and 10, 4 and 5. The only way I can get a plus 1 in here is if I have a positive 5 and a negative 4. I know some of you guys can already factor in your heads. That's awesome. These ones that are pretty simple like this, hopefully we can get along and get more of these to be able to be factored in your head. It's going to save you a lot of work in the end. If you need to take all the steps to get it correct, by all means, go for it. But this will save you a whole lot of work. Yes, factored form. Wonderful. Before you cancel, you need to find your points of discontinuity. Points of discontinuity are determined by whatever factors are in the denominator only. So only the denominator. I have x minus 4 is equal to 0. I solve, I get x is 4. Then I have to determine what kind of point of discontinuity that is. It's okay if you have to go back and check the notes a lot. So the notes say wholes are caused by zeros of the denominator that do cancel, and vertical asymptotes are caused by the zeros of the denominator that don't cancel. This one does cancel, so it's a whole. Right? X minus 4 and x minus 4 are the same. So I have a whole at x equals 4. Then where's my vertical asymptote? I don't have one. strangely, with all this work, horizontal asymptotes tends to be the thing that people pick up on last. I think because it's just so rule-based. So horizontal asymptote here, I've got x squared plus x minus 20. And in the denominator, I have x minus 4. But remember, I need to find the highest degree, and I need to make a match. So I have x squared on top, but I don't have x squared on bottom. So I'm going to write it in. I'm going to write in that missing term like we've been practicing. And then I'm going to take the coefficients. 1 divided by 0, that's undefined. It's not very clearly written. Let me try that again. So that means that there's also no horizontal asymptote. So this is not going to look like a typical rational function like we think of them. It's going to look nothing like the reciprocal function. So this graph is strange because I don't have a vertical asymptote and I don't have a horizontal asymptote. So let's go see what this graph looks like. Now, when you punch this in, you can always do in either factored form or the form that was given. Either way. Oh, wait. That's a different equation. Change this problem since I did it on my notes. What was it? X plus minus 4. Is that right? Okay. So this graph is just a line. Almost. Well, check out what happened, right? When I divided out the denominator, I was left with x plus 5. Right? This is the line x plus 5. The only difference, which you can't tell from the graph on here, is that I have a hole. We talked about that there's a hole at 4. So you can see that little open circle that it creates when I drag my, well, it's not even drag, when I click my pointer on it, 4 undefined. So this is going to be a line with an x-intercept of -5 and a y-intercept of +5 and a hole at 4. I did not draw my graph big enough. Let's fix that. All right, so I have an intercept here and an intercept here and a hole at 4, 9. definitely a different looking rational function. So it's interesting because this function right here looks like a really complicated graph. When I simplify it, I'm just left with y equals x plus 5. That's just a line. Slope of 1, y-intercept of 5. But this part that I crossed out that was making it a little more complicated creates this interesting little hole. So it's almost a line. Not quite. It does have a hole, which makes it a rational function. We're going to do one more. It's going to give us a little more practice with factoring and canceling and looking at different asymptotes. And then I have a worksheet for you that I want to give you time to start working on in class that you can give a couple of these some practice. Because they're a lot of work. I'm not going to lie. I feel like this lesson is one of the ones that brings together the most number of skills out of this class. All right, so one more. I've got more down here. There'll be just more examples for another day when we need a review and a refresher. So problem D, we're going to go for this one. This one's got, again, I know that they're all different. This one's got some additional pieces for the factoring portion. So D is f of x equal to 3x plus 3 all divided by x cubed minus 3x squared minus 4x. You can't even start this problem until you know how to factor. I'm going to pause here and I'm going to give you probably like a minute or two to do your best at factoring both of these. The top you can take out a GCF, the bottom you can take out a GCF, and then you have to factor the trinomial. Feel free to work together. Feel free to talk if you get stuck. But let's just focus on the factoring. Prior knowledge. Okay, when we factor the top, all you can do is take out a GCF of a 3. And I'm left with 3 times x plus 1. When I factor the bottom, I can take out an x as my GCF. And then when I factor this trinomial, I have x minus 4 times x plus 1. So when I rewrite this whole thing, I have 3 times x plus 1 divided by x times x minus 4 times x plus 1. If factoring is still a struggle for you, I would recommend going on Khan Academy or somewhere on the internet and finding additional factoring practices. You can find extra problems. I could probably assign some extra problems if you guys are looking for some practice. So now every factor in the denominator, everywhere I have an x, creates a point of discontinuity. So I actually have 3 this time. I have x is equal to 0. I have x minus 4 is equal to 0. And I have x plus 1 is equal to 0. 3 points of discontinuity. There's no limit to how many I could have. Well, x equals 0 is just 0. X minus 4 gives me a 0 at x equals 4. X plus 1 gives me a 0 at x equals negative 1. When I have factors that cancel, like x plus 1, that creates a hole. So I have a hole at x equals negative 1. Which means the other 2 points of discontinuity create asymptotes. I have 2 asymptotes this time. 2 vertical asymptotes. I'm going to pause and ask you to try to find the horizontal asymptote before I give it to you. So take a look at the rules, see what you need, see what you're missing, write it in. Hopefully you found that the horizontal asymptote is at y equals 0. Maybe. I don't have matching terms, right? My exponent with my largest term, my term with my largest exponent is cubed, right? I don't have that up here. It's missing. So now I'm going to take these coefficients, 0 divided by 1. So I get y is equal to 0 divided by 1, which is just 0. So the horizontal asymptote y equals 0, a vertical asymptote at x equals 0, and a vertical asymptote at x equals 4. And another interesting graph here. I've also got that hole, so after I draw my graph, I'm going to have to erase and kind of put that in. So you're going to have your device out to use Desmos, or if you have the Desmos app on your phone and you get service in here, then you can use that during the assignment. And I get this interesting looking graph that actually has 3 pieces. I think my hole was at -1. There it is. So I'm going to use kind of some pieces that I can find here. See a lot of easy points to graph on here. I think I'm just going to eyeball it. Let's see. This hits at 2 negative 0.75. It looks good. This piece kind of comes like this. Still has to stay within my borders of my asymptote. This one kind of comes like this. And this one, don't forget the hole. Like that. So while there's a lot of variation in what the graphs look like, the steps kind of follow the same. But that is an introduction to graphing rational functions using factoring.